Hello, we are discussing about gate lectures on digital circuits. Today we are going to discuss about counters. First you will see the difference between the asynchronous and synchronous counters, and then we will go for the design of asynchronous counters and how to obtain different modulus other than 2 power n. So these topics we will see. Now, we know that when counters are basically of two types, one is synchronous, the other is asynchronous counters. So let us see the difference between asynchronous and synchronous counters. So we'll start with asynchronous counters and synchronous counters difference. The basic difference is first one. Okay. In asynchronous counter, the external clock is only given to LSB flip-flop. For all other flip-flops, the clock is derived from the output of previous stage flip-flop. So if you think it is going to be a 3-bit asynchronous counter, 3-bit asynchronous counter means it consisting of 3 flip-flops, each can store a single bit, and these are outputs of asynchronous counter. And this is clock pulse for every flip-flop. Flip-flop is a sequential circuit which requires a clock pulse, and if the external clock is going to be given, external clock is always given to LSB flip-flop. Otherwise, by looking at external clock for which flip-flop it has connected, based on that one you can identify which is LSB flip-flop. If it is not given in the problem, you can identify the type of flip-flop where the external clock is connected in case of asynchronous counters. So let us assume the external clock is connected to this flip-flop. Say it is A and this is B, this is C. So output of A is going to be used for the clocking for the B flip-flop. That is, clock for B flip-flop is used from the previous stage flip-flop output, and clocking for C flip-flop is taken from the output of previous stage, that is B flip-flop. So like this, external clock is only applied to LSB flip-flop, so the flip-flop which is connected with external clock is always treated as LSB, and the last flip-flop is going to be treated as MSB. Okay, so this is asynchronous counter. Now, if we are going with a synchronous counter for the same 3-bit, for synchronous counters, clock is connected to all flip-flops simultaneously, because every flip-flop requires a clock pulse and external clock is connected to all flip-flops simultaneously. So now look at this one. All the flip-flops are going to be simultaneously applied with a external clock, and the outputs are going to be taken from the output of flip-flop. This is, so whereas it is A, B, C, and here it has to be mentioned in the problem that whether A is MSB or C is MSB. You cannot identify which is LSB or which is MSB until it is specified in the problem. So generally we assume that one in case of synchronous counters. Okay, the left hand side is going to be MSB and right hand side is LSB. Otherwise, based on the given problem, okay, that will be mentioned which is going to be used as MSB, which is used as LSB. Okay, so this is the first difference regarding clock. Okay, and second difference, since clock is only connected to LSB flip-flop, if you are applying a clock, that makes the output of flip-flop to change after some propagation delay. Okay, and this A, if it is going to be giving the clock, it is used as a clock for the B flip-flop. If it is generated the required clock edge, then B flip-flop gets changed after some propagation delay. Okay, and if B flip-flop is going to be getting changed such that it is making a clock edge for the C flip-flop, then the output of C flip-flop also changes after some propagation delay. If all are identical flip-flops with equal propagation delay, then the minimum propagation delay is 3 time periods for 3 flip-flop. Okay, if you are going for the 10 flip-flops, then in case of asynchronous counter it requires 10 clock pulses minimum. Okay, you must wait for 10 clock pulses, then only the output will be stable. Okay, so from this one we can say propagation delay required is more. So to get the output, the response of the input is produced at output after a long time. That is what we can say it as propagation delay is more. Propagation delay is more means, okay, we can say speed is less. The circuit operates at low frequencies. Speed is less. Okay, and whereas in this case, since the clock is connected to all flip-flops simultaneously, so all the outputs of flip-flop will change simultaneously. So you will get stable state within one clock period plus some additional gate delays. In the design, you may use some additional gates. So accordingly that design, you can get propagation delay as one clock period plus additional gate delays. So compared to this asynchronous counter, propagation delay is less. Propagation delay is less, and propagation delay is less means speed is more. That is, synchronous counters are faster than asynchronous counters. Okay, and third one, the design procedure. Okay, design procedure is simple. Design procedure is simple because directly you are connecting output of one flip-flop to the next flip-flop clock, output of next flip-flop to next flip-flop clock, like this. So that itself is going to making it act as asynchronous counter. Whereas here the design is going to be complex. Okay, it requires a few design steps to design for a required sequence. So complex design procedure. Complex design procedure. So the design procedure takes lot of time. It is time consumption. Okay, since you are taking longer time for the design, so that the propagation delay is less. Since you are taking less time in the design process, it is taking more time in the analysis. Okay, remember in that way. Complex design process. And fourth difference, mostly the flip-flops used in asynchronous counters are T flip-flop with T is equal to 1 and R JK flip-flop with J is equal to K is equal to 1. These are the flip-flops used in asynchronous counters. In asynchronous counters, for every clock, okay, what we estimate is the output of flip-flop will get toggled. Toggling of output is only possible in 2 flip-flops out of 4 flip-flops we have. We have SR flip-flop, JK flip-flop, D flip-flop, T flip-flop. But out of these 4, only T flip-flop and JK flip-flop will have the complement function. The other flip-flops doesn't have. Okay, so either T flip-flop with T is equal to 1 or JK flip-flop with J is equal to K is equal to 1 can be used in asynchronous counter design. No other flip-flops are suitable. Even though if it is suitable, it requires a complex design process for that one. Again, the advantage of third one, design procedure is simple, will get vanish. Okay, whereas in this case, any flip-flop can be used. Any flip-flop can be used for the design. Any flip-flop can be used for design. There is no restriction. And fifth one, and asynchronous counters cannot be used for generating random sequences. Okay, cannot be used for design of random sequences. Random sequences, whereas it can be used. So what is meant by this random sequence? If you are going to generate a sequence like this, first you have to get 1, then 4, then you are going with 2, then you are going for the 7 and the modulus ends. So the counter, the 3-bit counter, if it is passing through 1, 4, 2 and 7 states, then this is going to be a random sequence. It is not either in up count or in the down sequence. Then this type of generation of sequence is not possible with asynchronous counters. It is possible with synchronous counter. Even if you try to attempt, okay, then it takes longer time and the design process is very difficult compared to synchronous counters. So we never try this type of generating random sequences with asynchronous counters. Okay, and the last one, sixth one. Here, generally if you are going with a 3 flip-flops, then you may get different states. If you are using n flip-flops, then number of unique states you may get. Unique states is 2 power n. The possible number of unique states with n flip-flops is 2 power n, but most of the times we don't require all the states, we require lesser than that one. So we will go for the mod, okay, n counter. Mod n counter, most of the times n is going to be less than 2 power n only. Okay, don't confuse with this n and this n. So make it as mod m counter. Mod m counter. So m is going to be always lesser than 2 power n. It may be equal to m is equal to 2 power n. There is no design required. Directly if you are connecting in this way, then it can act as mod 8 counter. Okay, so if you require other than 2 power n mod, then we generally use preset and clear. Preset and clear, they are asynchronous inputs. They will be used in designing mod m counter, where m is less than 2 power n. Then these are going to be required. Otherwise, these two are this is not required. Either you can go with preset or you can go for the clear. Most of the times clear is more preferred than preset. Clear makes output of flip-flop to become 0, whereas preset makes output of flip-flop to become 1. Okay, so generally clear is going to be used whenever it is going for the initial state. We all expect that all flip-flops outputs are going to be 0, so getting resetted. So for that purpose clear is mostly suitable, but preset is also used in case of down counters where the initial state is all ones. Okay, and here no need to use asynchronous inputs like preset and clear, because the design procedure will take care of all these things. That is, modulus of n can be taken with the help of design procedure, okay, as well as random sequence can also be taken by the design procedure. So no need to use asynchronous inputs for the synchronous counters. So these are the basic differences between asynchronous counters and synchronous counters. Okay. Now we discuss about 3-bit asynchronous counter. So say it as 3-bit asynchronous down counter we are going to discuss. And as we know, in asynchronous counters, either T flip-flop or JK flip-flop are going to be used, and whichever flip-flop is used, all the inputs must be connected to logic 1. So this is a simple diagram which I have taken using T flip-flops. Okay, so this is a 3-bit asynchronous down counter. How it is performing down operation and how to make it to convert to use as up counter. Okay, and how can we identify by looking at the circuit diagram whether it is performing up operation or down operation, that also we are going to discuss. Okay, so first of all there are T flip-flop is used, and we know that one T flip-flop truth table is T, and this is Q plus is output, that is next state of T flip-flop. Flip-flop is a sequential circuit where the next state depends on present state and present input. So for a T flip-flop, T is a present input, Q plus is next state. If T is equal to 0, next state is same as present state. If T is equal to 1, next state is complement of present state. So here we are going for this procedure. T is equal to 1. Always T is connected with logic 1. Are you looking at the T flip-flop? T is connected to logic 1 for all the flip-flops. So we are only considering about this row. Whenever T is equal to 1, Q plus is equal to Q bar. Okay, but the word statement of t is equal to 1, next state is complement of present state, is going to be a little bit confusing. We can always say even if t is equal to 1, output will not toggled, that is will not get complemented until there is a desired clock edge occurs. Because they are all sequential circuits, they all perform, that is output depends on inputs on clock edge. So since you are using a clock, that clock is of positive edge clock, so that here we are using a positive edge clock, and this positive edge clock means whenever a positive edge occurs for this flip-flop, then since t is equal to 1, output will get complemented, that is next state is complement of present state. And for this flip-flop also, if you get positive edge over here, that is next state will be complement of present state, otherwise next state will be same as present state, because if toggling is not taking place, then it will retain the previous state information. So next state will be equal to present state. Okay, so now first identify which flip-flop will be treated as LSB. Okay, say this is a flip-flop A, and this is B, and this is C. For asynchronous circuits, always external clock is connected to LSB flip-flop. So by looking at which flip-flop is connected with external clock is this one, that is connected to A flip-flop. So A will be treated as LSB flip-flop, B is next one, and C is the last flip-flop. Last flip-flop is treated as MSB. Okay, so now I am going to write one important point which will be used in entire design of counters. Okay, whether it is sequential or whether it is synchronous or asynchronous. Look at this one. When this output will toggle, that is flip-flop C output will get complemented, that is toggled only when this is positive edge triggered. Positive edge trigger is 0 to 1 change. 0 to 1 change you can write like this. This is 0 and it is 1. 0 to 1 change is nothing but making a positive edge. So whenever there is a 0 to 1 change occurring at the clock input of C flip-flop, and clock input of C flip-flop is deriving from B flip-flop output. So whenever QB is changing from 0 to 1, when QB is changing from 0 to 1, that makes to appear a positive edge at the clock of C flip-flop, which makes the toggling of the flip-flop C, that is output gets complemented. Remember this one. In all other cases, output will remain as it is. And if you are coming for a B flip-flop, okay, output of this flip-flop will get complemented. Output will be toggled, that is gets complemented only when clock is changing from 0 to 1. Again, clock is changing from 0 to 1 means output of A flip-flop changing from 0 to 1. So QA is changing to 0 to 1. Then what about this one? Okay, then we are going for the last one. For this last flip-flop, output gets toggled. Output will be toggled only when clock is changing from 0 to 1. External clock is changing from 0 to 1. Clock means you are applying one clock, means you have applied one complete cycle. That one complete cycle, if you observe, okay, this is a clock pulse. One complete cycle you can say in this way. Starting point of this one, and this is the ending point. Okay, so this is starting point and it is ending point. Otherwise you can start from this point, you can end at this point. That is called as complete cycle. Every complete cycle, if you observe from this point to this point, so that will be having a positive edge, that will be having a negative edge, as well as active high as well as active low. So one complete cycle will consisting of all different edges, positive edge, negative edge, and active high enable, active low enable. Okay, so here this flip-flop requires only positive edge. That positive edge is definitely given during a one complete cycle. So that implies nothing but output will get toggled when. Okay, not only when, we can write like this: output will be toggled for every clock pulse. For every clock pulse. Since every clock pulse is nothing but complete cycle. That complete cycle is going to be giving all types of edges, and the required one for this is positive edge. So definitely we are going to get positive edge for this one. So definitely output will toggle for every clock pulse. This is very important. Okay, so even though t is equal to 1, output will not toggle, and it wait for a clock edge. After getting the clock edge, if t is equal to 1 at that time, then the output will be get toggled. Remember this one. So this information I am going to use for the operation of 3-bit asynchronous down counter. Okay, now we will see the operation of 3-bit down counter. So first I am writing the MSB flip-flop, later I will go for the LSB. So this is what I am going with. First assume that we are applying a clock pulses, and afterwards we will go for the QC, QB and QA. So initially if you are not applying any clock pulse, we assume that the flip-flop, all the flip-flops are resetted, so that initially they are at 0 0 0 condition. Okay, now you are applying a clock pulse. Whenever a clock pulse occurs, at that time LSB flip-flop, which is nothing but QA, this is LSB and it is MSB. LSB flip-flop will get toggled for every clock pulse. So this is getting toggling. Toggling means present state is 0, so complement of that one is 1. And this 0 to 1, okay, look at this one, 0 to 1 change, which is nothing but like this. So 0 to 1 is always treated as positive edge. 0 to 1 is always treated as positive edge. That positive edge is generated at output of flip-flop A. That positive edge is given as the clock for the flip-flop B. So flip-flop B gets toggled. So previously B is having 0, now it will be changes to 1. And this again it is going to be 0 to 1. 0 to 1 means positive edge. As it is positive edge, okay, that makes QC to toggle. So QC is also getting changes to 0 to 1. Since this is the last flip-flop, output will be kept as it is. It will not be clocked used for the clocking of other flip-flop. So the state upon application of first clock pulse, the steady state what you are going to get is all ones. And next apply the second clock edge. Okay, you should not apply the second clock edge until the outputs are going to be coming into steady state. That is, until all the flip-flops are getting changed and they have come to steady state, then only you can apply the second clock pulse. So even though you are applying a clock pulse, that will make change at the output of flip-flop A, and that may become that may be possible to get a change in the output of flip-flop, and that may change. There is a possibility that may induce a change in the output of C flip-flop. So you must wait until all these transitions are going to be taking place. Then only you can apply the second clock edge. So now you are applying second clock edge. Okay, that's why only it is taking more propagation delay. Speed is less for asynchronous counters. Now come for the second one. If you are applying second clock, then this 1 to 0 toggling is taking place, but 1 to 0 toggling is negative edge. 1 to 0 is nothing but like this. 1 to 0 negative edge you are applying, but negative edge, for negative edge flip-flop B doesn't respond, because B and C, A, B, C are positive edge flip-flops, so it will remain the previous contents. So next state is same as present state is 1 you are going to get, and 1 to 1, that is no transition even, that is you are not applying any clock pulse, so QC also remain with the same content. 1 1 0 is going to be the now state. If you apply third clock pulse, again 0 to 1, LSB flip-flop will change 0 to 1, which is positive edge. So output will get toggled of B flip-flop. So 1 to 0. 1 to 0 is negative edge. So C flip-flop doesn't change. Next. For fourth flip-flop, LSB flip-flop always gets toggled 1 to 0. This is negative edge. Negative edge doesn't induce any transition in the QB. So that QB remains same. And QB is not providing any clock edge for the QC. So QC remains same. Next, fifth clock edge. If you apply fifth clock edge, again LSB flip-flop gets toggled 0 to 1. It is positive edge. So this will become 0 to 1. Again this 0 to 1 is positive edge. That positive edge is for the C flip-flop. So C flip-flop gets toggled. So 1 to 0. Now the flip-flop contents are 0, 1, 1. Apply sixth clock edge. This 1 to 0. 1 to 0 is negative edge. So it doesn't change. It doesn't change. And next, seventh one, 0 to 1 change. 0 to 1 is again it is positive edge. The positive edge is connected to clock of QB. So QB gets toggled 1 to 0. 1 to 0 is negative edge. So QC doesn't respond. Next, eighth. If you are applying eighth one, 1 to 0 it becomes. Okay, 1 to 0. 1 to 0 is negative clock edge. So for negative clock edge, QB doesn't react and QB not providing any clock for the QC. So QC doesn't react. And if you are applying ninth clock pulse, again 0 to 1 transition takes place. This 0 to 1 transition is positive edge and this positive edge is used for the clocking of QB flip-flop so that QB gets toggled. So again it is changing from the 0 to 1. That is next state is complement of present state. So present state is 0, you are writing next state as 1. 0 to 1 is again positive edge. So this is again positive edge which is clocking the C flip-flop. So C flip-flop also changes 0 to 1. Okay. So now if you apply 10th clock pulse, again you are going to repeat the same sequence. So this will become 9th one, 9th state and 10th clock pulse, 11th clock pulse, 12th clock pulse, like this you will get 13th, 14th, 15, 16, 17. Okay, and if you are writing for the next again and again you are applying clock pulses, then it will become 18th clock pulse, 19th clock pulse, 20th clock pulse. Okay, so you can apply any number of clock pulses, but since it is a 3-bit counter, it can accommodate only 8 unique states. Those 8 unique states are going to be getting repeated if you apply more than 8 clock pulses. That's why sequential circuits are cyclic in nature. Sequential circuits are cyclic in nature because the flip-flops used in sequential circuits are going to be constant. Based on that constant number of flip-flops, you are going to get a constant number of states, and if you apply more clock pulses than this number of states, then definitely it has to repeat those number of states. Hence, the sequential circuits will be cyclic in nature. And if for this one, you may be asked a question that one, what will be the content of this 3-bit asynchronous down counter when the clock pulses, when 22 clock pulses are applied? That is, after application of 22 clock pulses, what will be the content present in the flip-flops? So 22 clock pulses is, you have to write it as 21 and this is 22. After application of 22 clock pulses, you are going to get 0, 1, 1 as the answer. You will be asked, okay, what will be the content of this counter after application of 15 clock pulses? After application of 15 clock pulses is 0, 0, 1. After application of 10 clock pulses, 1, 1, 0. Like this you may be asked the questions. Okay. Now if you observe, as the clock pulses are going to be increasing, the content in the flip-flops is going to be reducing. 1, 1, 1 is 7, 1, 1, 0 is 6, 7, 6, 5, 4, 3, 2, 1, 0. So it's called as down counter. And modulus of this counter, modulus means number of unique states the counter can reside in. Okay, how many number of unique states this counter is producing, that will be generally treated as modulus or simply mod. Since it is providing 8 unique states starting from 1 to 8. Okay, 1 to 8 clock pulses, again 9 to 8, 9 to 16 is same as 1 to 8, again 18 to 24 is same as the previous 1 to 8. So it is providing 1 to 8 as unique states. Okay, 7 to 0, where so this is going to be called as modulus 8, or simply it is mod 8 counter, mod 8 down counter. Okay, mod 8 down asynchronous counter. These asynchronous counters are also called as ripple counters. Okay, so whenever there is a positive edge and the clocking is from the output of flip-flop, then the circuit works as down counter. Okay, now we will see one more important concept behind this one, behind this operation. Now we will discuss about the one more important concept of this operation of 3-bit asynchronous down counter. That is, we are going to derive frequency at each output of flip-flop. Okay, what will be the frequency at QA? What will be the frequency at QB, QC with respect to clock pulse frequency? Okay, so for that one, the same operation whatever we have discussed, the table form I have written it as timing diagram. So initially, for whenever you are not applying clock pulse, by the time QA, QB, QC all are resetted, and QC is MSB, QA is LSB. This is A and B, C. So whenever the first clock pulse is applied, at that time under steady state you are going to get 111, which is nothing but 7, and next it is going into 6, 5, 4, 3, 2, 1, 0 as you are increasing the number of clock pulses. This is total count. Okay, so QC is MSB and QA is LSB. Next, assume that one we are applying a clock. So frequency of clock. So F clock is given as 8 hertz. What is meant by this 8 hertz? What are the other units for the hertz? 8 cycles per second. So you will get within 1 second, if you are getting 8 complete cycles, then the frequency of that clock is 8 hertz. 1 kilohertz means 1 cycle, 1000 cycles per second. 1 megahertz, 1 mega cycles per second. Okay, so here for 8 clock pulses, we can say that 8 complete cycles you are getting within 1 second, that is nothing but 8 hertz. So I am making the frequency is equal to 8 hertz. So I am indicating till this 8. Okay, this is the duration of 1 second. 1 second duration. In this 1 second duration, you are getting 8 complete cycles. 1 complete cycle, 2, 3, 4, 5, 6, 7, 8. So that since 8 cycles within 1 second, clock frequency is 8 hertz. Okay. Now, what will be the frequency of QA? QA is getting toggled for every clock. Okay. So since for every clock edge, QA is getting toggled. So first QA is getting toggled for first clock edge 0 to 1. Next clock edge it is changing to 1 to 0. Next it is changing from 0 to 1, 1 to 0, 1 to 0, like this, 0 to 1, 1 to 0. So QA toggles for every clock pulse. Whenever it is toggling for every clock pulse, how many number of cycles you are getting for QA? Number of complete cycles within 1 second. This is 1 complete cycle, okay, from this point to this point, and this is second complete cycle, third complete cycle, fourth complete cycle. So 4 cycles per second for QA, which is nothing but 4 hertz. 4 hertz is the frequency of QA, which you can write it as simply clock divided by 2. Okay. Similarly, if you are checking about QB is 1 to 0 change and 0 to 1 change, 1 to 0. So this is 1 complete cycle. Okay, and one more complete cycle is this one within 1 second duration, whereas QB going through only 2 complete cycles. So 2 cycles per second. So 2 hertz, that is frequency of QB. So which is nothing but frequency of QA by 2, that you can write as frequency of clock divided by 4. And if you are looking at the QC, that is MSB, which is changing only from 1 to 0. So this is only having 1 cycle. 1 cycle per second. So that is 1 Hz, which is frequency of QC flip-flop. So you can write as QB by 2 or QA by 4 or F clock divided by 8. So this is a relation between frequency at the output of each flip-flop with respect to clock. Okay, and that's why only, since it is mod 8 counter, this is very important, it is specified as mod 8 counter since it is going through 8 unique states. Mod 8 counter. Mod 8 is also called as divide by 8. Divide by 8. Why it is called as divide by 8 counter? Okay, divide by 8 counter, because if you are looking at clock frequency and at the output frequency, this is what MSB flip-flop. Okay, so the frequency at this QC is going to be F clock divided by 8 or not. So this can be written as F clock divided by 8 means mod 8, because it is going through 8 unique states. So output frequency is divided by mod times with respect to clock. That's why if you are saying mod 8 counter, output frequency is 8 times less compared to clock frequency. If you are saying it as mod 12 counter, output frequency is 12 times less compared to clock. Okay, so that's why mod 8 means divide by 8, mod 10 means divide by 10, mod 15 divide by 15, mod n counter, so divide by n counter, divide by n counter, which is nothing but simply it is mod n counter. Okay, this is one important point. And next important point is, if you are only going through a single T flip-flop, if you are going with a single T flip-flop where T is always connected to 1 and there is a clock pulse you are applying and you are going to check about Q value. So frequency at Q is always equal to F clock divided by 2. Whatever the frequency you are applying at clock edge, that will be divided by half. So a single T flip-flop. So hence a T flip-flop with T is equal to 1 or JK flip-flop with J is equal to K is equal to 1 can act as divide by 2 counter. Divide by 2 counter. Okay, the meaning of divide by 2 counter is nothing but output frequency is half of input frequency. Output frequency is half of input frequency. So if you observe, if you are only going to A flip-flop, okay, A flip-flop is nothing but here the clock frequency is 8 Hz and output frequency is 4 Hz, because half of this 8 is 4, because clock frequency we know 8 Hz and single flip-flop is going to be used as divide by 2 counter. So output frequency is divided by output frequency is half of clock frequency. So 8 by 2 is 4. Now this 4 Hz is going to be act as input for B flip-flop. So now clock frequency is 4 Hz for B flip-flop, and since this T flip-flop is going to be acting as divide by 2 counter as it is connected T is equal to 1. So this Q is frequency at Q becomes half of clock frequency. Clock is 4 Hz, so you will get it as 2 Hz. Now the 2 Hz is you are applying it clock input of C flip-flop. So since T is connected to again logic 1, so again this act as divide by 2 counter. So output frequency is 2 by 2, which is nothing but 1 Hz. Like this also you can think. Okay, so each divide by 2, you are connecting 3 divide by 2 counters. You are connecting 3 divide by 2 counters, divide by 2, divide by 2, divide by 2 counters in cascade. In cascade it will get producted, it will be get multiplied like gain. Okay, if you are making cascading of amplifiers, gain increases. Okay, if you are going for the 3 amplifiers in cascade, total gain is nothing but multiplication of all those 3 amplifier gains, A1, A2, A3. Similarly here, modulus 2, modulus 2, modulus 2, 2 into 2 into 2 is mod 8. Okay, so you may be asking about the other types of different questions you may expect is what will be the output frequency if the clock frequency is given. Otherwise, if the frequency at B flip-flop is 2 Hz, what can be the clock frequency of the given circuit? You are given the same this circuit. Now it has given that. So we will go in this way. The expected questions may be in this. So let us assume you are given this given this diagram, and it has given that one. If the frequency at Q is 2 Hz, okay, then what is the clock frequency? Find the F clock for the given circuit. So since T flip-flop is acting as mod divided by 2 counter, definitely clock frequency is twice of output frequency 4. So this is output frequency, so you must get it as 8. Otherwise, if it is given as output frequency is something as 16 Hz, then what will be the frequency at Q0? FQ0. So 16 by 2 8, 8 by 2 is 4. So we will get 4 Hz as answer. Okay, sorry, this is wrong. 16 Hz, 16 is nothing but it is twice of this one, this is 32, and you will get it as 64. So FQ0 is 64 Hz. So don't confuse. So this type of questions you may expect. Okay. So till now we discussed about the 3-bit asynchronous down counter, and this is a circuit diagram of that one. Now how to convert this circuit diagram into 3-bit asynchronous up counter. Asynchronous up counter. So what modifications if you make, then the circuit act as asynchronous up counter of same 3-bit. Because this circuit diagram already we discussed, which is acting as down counter. Now we want to make it as up counter. Okay. In what ways you can make this circuit to work as up counter, that we are going to discuss now. Okay. So down counter is performing since the clock is connected to the LSB flip-flop, and the clocking for the others are going to be taken from the output of flip-flop. Okay, look at this one. And next, one way of doing it is, instead of making positive edge clock, change to negative edge clock. So remove the clock. Okay, first possibility means, okay, remove positive edge clock and connect a negative edge clock. If the clock is negative edge type, so I am going with in this way. If it is, now it is negative edge clock. So if it is negative edge clock, then it acts as up counter. So 3-bit asynchronous up counter, now it will perform. Next, otherwise, what is the other possibility is, instead of taking clocking for the other flip-flops, previously what you have done, clock for the B flip-flop is taken from the output of A flip-flop. Instead of taking output of A flip-flop, if you are taking from the complement of A flip-flop, that is complemented output of A flip-flop is going to be used for the clocking for the next, then it acts as up counter. This is another way. So we no need to change the clock now. For the same positive edge, it acts as up counter if you are taking clocking instead of taking from Q, if you are taking from Q bar. So look at this diagram. You can identify the difference. Okay. Now clock is positive edge only. Okay. And now instead of taking from Q, we are going further from the Q bar. So Q bar of A flip-flop is act as clock for the B flip-flop, and Q bar of complemented output of B flip-flop is act as clock for the C flip-flop. Then also it can act as up counter. Okay, and you can simply analyze this circuit because it is a positive edge triggered circuit, and output of C flip-flop will be get toggled whenever B flip-flop Q bar is changing from, okay, B flip-flop output is changing from 0 to 1. 0 to 1 means Q has to change from 1 to 0. whenever the output of B flip-flop is changing from 1 to 0, then the Q bar is changing from 0 to 1. That is the required positive edge for C flip-flop, so that the output gets toggled. Similarly, B flip-flop output gets toggled for positive edge clock, which is 0 to 1. 0 to 1 you are expecting for the clock edge at B. That clock edge you are taking from Q bar. So Q bar has to change from 0 to 1. That means Q has to change from 1 to 0. Okay. So simply this is the meaning is, as you are taking from Q bar, okay, clocking from Q bar, that is you are taking negative edge from the Q. Negative edge from the Q. So you have taken, either you can change over here or you can go for this way. In both cases, this circuit acts as asynchronous up counter of 3-bit nature. Okay, and you will get the same timing. You will get the timing diagram as like this. This is the timing diagram. This timing diagram is valid for both. So initially, if you are not applying any clock pulse, then outputs are resetted of all flip-flops after application of first clock pulse 1, 2, 3, 4, 5, 6, 7, 8. 8 clock pulses we applied. So after application of first clock pulse, only QA gets toggled. So this will become 1, 0, 0. And remember that one, while writing, this is MSB and it is LSB. So you must write count as like this: QC, QB and QA, because always we will write MSB on the left hand side, LSB on the right hand side. Okay, so QC, QB, QA. So the count is 0, 0, 1, whose the count is indicated over here 1. And next this 1 will get changed 0, and this is 1 and it is 0. Output of QA is changing from 1 to 0. Output of Q is changing from 1 to 0. That makes a positive edge at Q bar. Actually 1 to 0 is negative edge. So at Q bar you will get positive edge. That positive edge is clocking the B flip flop. So that B will change from 0 to 1. 0, 1, 0. So next you will go for 1, 1, 0. So this is next for 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And again it is back to 0, 0, 0. Again the modulus for this one is, modulus is 8, which you can write it as mod 8 up counter. Mod 8 up counter. So it is going through 8 unique states in upward direction. So starting from 0 it is going towards till 7 and again it is coming back to 0. Okay. And same flip-flop, T flip-flop act as divide by 2 counter. It is irrespective of clock edge. Clock may be positive edge or negative edge. Okay. So T flip-flop act as divide by 2 counter. So f of QA, you can write it as f of QA is equal to f clock by 2, and f of QB is equal to FA divided by f of QA divided by 2, which is nothing but f clock divided by 4. Otherwise f of QC is equal to f of QB divided by 2, which is QA divided by 4, that is equal to f clock divided by 8. For the same reason, okay, output frequency at the MSB flip-flop is divided by modulus times with clock frequency. So clock frequency will be divided by modulus times and it will be appear at the output of MSB flip-flop. That's why it is called as mod 8 counter, or mod 8 is also called as divide by 8 counter. So till now what we have seen is, we have seen about the differences between asynchronous and synchronous counters. Later we started discussion with asynchronous counters. In asynchronous counters, we have seen that one either T flip-flop with T is equal to 1 or JK flip-flop with JK are connected to 1 are going to be used, because only in those two flip-flops toggling is going to be possible. Okay, and for the operation of asynchronous counter, you must, and whatever it is, asynchronous or synchronous, for the operation you must know output will change, okay, only when clock edge occurs. whether the input changes or not, it doesn't matter. Okay, output directly doesn't depend on input. Output will depend on input only when clock edge occurs. Otherwise output will be same as previous state. If you understood this concept, then analysis of asynchronous counters is going to be very simple. Okay, so first we analyzed the down counter with a circuit diagram, and later how to convert that down counter into up counter. Okay, so from this one I am going to conclude two important things. Okay, so when you will get a up count, when you are going to get a down count. If, okay, look at this one, if clock is having positive edge, if clock is positive edge and okay, clocking for next flip flops, clocking for higher order flip flops, clocking for higher order flip flops are taken from Q, that is output of flip flop, uncomplemented output of flip flop, then it is down counter. Otherwise, okay, if clock is negative edge and you are taking clocking from Q bar, then also it is down counter. Okay, now if clock is, look at this one, if clock is negative edge and the clocking for the next higher order flip flops is taken from Q, clocking for the next higher order flip flops are taken from the Q off, that is uncomplemented output from the previous stage, then it is up counter. Otherwise, if clock is positive edge and if you are clocking for the higher order flip flops are taken from complemented output of flip flop, then it is up counter. So if you are taking clocking from the Q bar, then it is called as up counter. So up counter can be possible in two ways, down counter can also be possible in two ways. Okay, and in next class we will see how to get the modulus, desired modulus other than 2 power n. Okay, thank you.